not. So the recollection is from watching David. Don't stand too close and get into fiction. So I want to talk about line locking in observational quasars and quasars in general. But I want to first motivate why I'm talking about this. Now, I was asked, have I worked on this? And the answer was not really, but about 6 months ago, or like that a year ago, I was asked to referee a paper on line locking in quasars by Dorlan, Sholosh, and students. Now, Dorlan was a postdoc here 10 years ago. And so I looked at the paper and looked at their arguments. They did a good job. So I recommend that it be published. But it got me thinking about line locking. They referred to a couple of observational papers, which I hadn't paid any attention to. I'm going to talk about it. The reason I want to talk about it is I want to motivate it from the point of view of galaxy formation. Okay. So, right, as you know, many of you, but many of you might not, galaxies are collections of stars. Okay. Typically 10 to the 6 to 10 to the 12 solar masses of stars. And the ones we normally think of, like the Milky Way, they have 10 to the 11 solar masses of stars. Okay. And they sit in, now, dark matter halos, as they're called. And the reason we know that is because if you look at the rotation curves of galaxies, they're sort of these galaxies that are classically flat, so like 200 kilometers a second, 220 kilometers a second, certain velocity, out to 50, 60, 70 kiloparsecs, where there aren't any stars, right? The typical size of a galaxy is maybe exponential scale of stars in numbers 3 or 5 kiloparsecs. The half-life radius is a little bigger than that, right? Not much. And so the fact that, and the gas is the same way, most of the gas is inside, say, 10 kiloparsecs. You can see it, I think it's H1, way out, like I said, 50, 60, 70 kiloparsecs in some cases. But there's not a massive gas in stars to produce a circular velocity of 200 kilometers a second at 50 kiloparsecs. So there's got to be something else, which we call dark matter. And then we talk about dark matter halos because that's supposedly the region around which the dark matter has roughly been virialized, meaning it's not just going in straight lines or whatever, it's going around orbits. Orbits, we don't actually know what they are. They're roughly, the shapes of the halos we know are roughly spherically symmetric, not quite. And they look like they're virialized, meaning that the particles are gravitationally bound and their kinetic energy is like half of their potential. Okay, so that's a dark matter halo. They're typically like the Milky Way, 200 kiloparsecs. Right. So that's what a galaxy is. It's something that's like sort of 10 kiloparsecs or less the size of stars. And it's stuck pretty much at the center. We think of a thing that's like 10 times that size, 100 or 200 kiloparsecs, made out of 10 times as much stuff. Typical halo mass for the Milky Way galaxy is 12 masses. But then there's a funny thing. I mean, and of course, there's more little stuff than big stuff. That's sort of generic. So there's more low mass galaxies, galaxies. But if you go to high masses, there's a pretty sharp cutoff. Okay. At around 10 to the 12 solar masses of halos, or 10 to the 11 solar masses of stars. So that's called an L star galaxy. That's the characteristic break luminosity, mass, and stellar mass, because the mass light ratio of stars is about 1 solar units. Okay. And so this raises the question: there are bigger halos, we know that. They tend to have a lot fewer stars relative to their stellar dark matter halo mass. Okay. And one explanation for this is that there's some form of feedback that prevents the gas in those halos from turning into stars. Now, in fact, if you look at really big halos, 10 to 15 stars, you actually see that all the baryons correspond to that 10 to 15 solar masses. It's actually in that halo. You can see it primarily from X-ray objects. And then there's a tiny little bit of stars, like 10 to 12 solar masses. So there's plenty of gas around, but it's hot. It's the real temperature of those halos, which is 1,000 kilometers a second, 10 to 17 Kelvin, which is why you see it in X-rays. Okay. But why didn't gas turn into stars? Well, one reason is because it's too hot, and cooling time is long, it shouldn't turn to stars. I don't want to get into that big story. That's feedback on really big halos. I'm thinking about feedback halos that are a little bigger than 10 to the 12, that also don't form that many stars. Right? So that's sort of the motivation for line locking. It has to do with feedback. What the hell does that have to do with feedback? That's going to be popular. Now, even at 10 to 12 solar mass halos, some of the galaxies you see are blue because they're making stars. And some of them are red because they stop making stars billions of years. And those, the latter galaxies are said to be quenched. Right? And that's believed to be due to some form of feedback. Probably with black holes, possibly from stellar feedback. There's also another form of quenching, which is if you're in a cluster of galaxies in your 10 and 12 galaxies, when you fall into that cluster, there's this hot gas I was just describing. That can strip the gas out of the galaxies, fall into it, and that also turns them on. Okay. That's pretty easy to understand. In the case of clusters, you do see a lot of red spirals, spiral galaxies, that are in star forming. But you also see red spirals just in the field. They're not things that are high intercluster. And for those things, people think that there's some form of feedback that gets rid of the gas and stops the starting. Right? Now, there's sort of two good sources of this feedback. One is stars, supernova. And we know that works for lower mass galaxies. Certainly, if you believe all the fire sequences, lower mass galaxies, but observations. Another form, though, is feedback from black holes. Okay? Because if you look at most L-star galaxies, they have supermassive black holes. Right? Now, you can ask yourself, well, could the black holes have done this? So energetically, the answer is there's no question. So if you look at an L-star galaxy, so the properties, as I said, the halo mass is of order 10 to the 12 solar masses. Stellar mass, so 11. The radius of the halo, the virial radius is sort of 200 kiloparsecs. Sort of the effective radius or half-life radius of stars. That's typically 5 kiloparsecs, or maybe 10, some number like that. There's also gas in these things. Okay. And it's typically, if you count both the atomic and molecular, it's around 10 to the 10 solar masses. Right? And of course, one obvious way to stop star formation is to remove fuel, and this is the fuel, so get rid of the gas, you can stop the star. Okay. So energetically, what would that require? Well, I haven't said here, but you can work it out from, for example, this number plus that number, what the circular velocity is. Okay. And I mentioned it earlier, right? The circular velocity of an L-star galaxy is like 200 kilometers. Okay. And as I said, this rotation curves tend to be flat. So isothermal spheres, so the mass as a function of radius is just proportionate to the radius. Okay. All right, now suppose you want to remove all the gas from that radius. Okay. So I need Gm of at that radius. Times the mass in gas at that radius divided by R, potential energy. Well, this is just E circular squared times the gas mass. Okay, so that's how much energy. So we could just plug in these numbers. This is 200 CGS units. It's 2 by 10 to the 7. You square that. And that gas mass, solar mass, that's 2 by 10 to the 43. That's 8 times 10 to the 37. So just call it 10 to the hertz. Okay, something like that. If you want to just take each atom and leave it out, that's what. Well, can you do that with a black hole? Well, it depends on how big a black hole is, right? So what do these things look like for L-star galaxies? Black holes. Most galaxies that are L-star have supermassive black holes, and we've got one that's a few by 10 to 6 solar masses. Some of them are like nearby things like see for galaxies like NGC 5548 is probably 10 to the 8 solar masses, so it's in that range. Okay. So in L-star galaxies, you have black hole masses, like I'll call it 10 to the 6 to 10 to the 8 solar masses. Or even bigger, they can be up to 10 to the 9. Okay. Well, how much energy was released when we built that black hole? Okay. Well, the total binding energy is roughly just the mass of the black hole times c squared. But typically, the efficiency of getting energy back out when you put stuff in is not 1. Still have the mass sitting there, but it's some fraction. Usually, people like to call it something. It's some number like a 10th. Okay. So let's use, the Milky Way's black hole, 4 by 10 to 6 solar masses. Okay, that energy is 0.1. It's at 4 by 10 to the 6. CGS. That's about 10 to the 21. Right? 3 by 10 to the 10 squared. Well, 4 times 2 is about 10. So that's 1. And so this is 10 to the 54. 10 to the 60. Okay. So just from that really crude calculation, yeah, there's plenty of energy when that black hole is assembled to eject all the gas. No problem. So that's why people think black holes are attractive sources. Now, of course, that's not really the right thing to do because it takes a while to assemble the hole. And while you're dumping all the energy out of the hole into the gas in the meantime is also okay. So what you have to do is you have to dump that energy into the gas. Well, the first thing you have to do is dump it in a timescale shorter than dynamical time. It'll take you a dynamical time to move the gas out. Right? You really have to do it on shorter than the cooling time of the gas. And that turns out pretty hard to do for these numbers. Cooling times tend to be pretty short in the Milky Way. Even at the mean density in the disk, let's say 1 particle per cubic centimeter, the cooling time, right, it's lambda, the cooling function. It's about 10 minus 22 at best, 10 minus 23 if you're lucky. And then if you take lambda, NENP, for example, that'll give you a rate. It's 10 minus 22 times NENP, that's per square centimeter. If you're in denser gas, well, what you want to do is you want to compare this cooling time scale in a disk to the rate which you're putting energy out of this thing. And if it's near Eddington, this cooling time, even though that's sort of mass, is going to be shorter. So the gas will sit there and stay cold. So
I guess, outflow. And it's outflow.
An outflow from what?
If the outflow, imagine you have one.
Yeah.
It's outflow.
Yeah.
And then, because it's mass.
Yes.
There's these temperatures go.
Yes.
So cooling is suppressed.
In the outflow, once you got it going,
once you know.
that's the difficulty is getting it going. Right? If you just, for example, shine light onto the gas, which is what the quasar does best, right? Most luminosity of an accreting black hole, if it's near Eddington, comes out as light. If these big holes, it's in the UV. So that'll heat the gas up. If you, for smaller holes, it comes out as X-rays. Then you'll heat up gas to basically the constant temperature or close to that. You get things up to 10 to the 7. Right? This velocity corresponds to temperatures of 10 to the 6 to 10 to the 7. So you'll heat up gas. You have to heat the gas up to that temperature. The difficulty is getting past the bump in this cooling function. The cooling function is like this. And this is just 10 minus 22 in the units of centimeters cubed per second. Okay. And this is typically around 10 to the 5 delta. Okay. This is log. Okay. Log. Okay, so that's what it looks like. So what you have to do is you have to heat it faster than this. Okay, and that typically takes a luminosity that's bigger than 10 to the 46 thirds a second, which is the Eddington luminosity for that mass. So it's hard to see how a normal quasar can drive gas out by heating it. Now, as Chris says, if you have a wind, you can do it, right? And so part of this talk is, I'm not going to get there real fast at this rate, but there are winds. We see winds coming out of quasars. So that'll be one of my favorite mechanisms for heat. Okay. All right. So
You assume implicitly like
optically thin. Yeah. Which is not great for the ISM of the galaxy. Yeah, you'll just heat up the inside skin of it. That's correct. And you'll drive a wind off of there for heat, which is probably happening. It's hard to get all the gas out of the wind, just from the start. You can get a certain mass loss rate. It's hard to get all the gas. Now, the other thing you can do is, this is an energy argument. The other way you can do it is push the gas out, as Chris was sort of hinting at. So what do you have to do to push the gas? Well, this is an energy. You can also write this as a force, right? The force on gas particle in the galaxy is that same expression. That's on there for a moment. Divided by r squared, right? Okay. Because gas is that. So that's E circular squared times m gas of r over r. That way. So unless you push harder than that, you're not going to get the gas out. Okay. So you have to push that hard. Now, if you take the luminosity of the quasar, like if you're trying to use light or anything else that comes out of it, actually, right? Luminosity is just an energy. If you use light, then the force exerted by that light. Well, so let's go back a second. That's the mass of the black hole. If it's just sitting there, of course, not accreting anything, black holes are going to be many together. And the best evidence for that is our own Milky Way, where you got this pretty big hole, 4 by 10 to the 6, and maybe it produced the Fermi bubbles, and maybe it didn't. But the Fermi bubbles didn't do anything to the galaxy. But of course, the reason is because the thing's accreting at like 10 minus 7 Eddington. Well, let's assume you do more or less the best you can do, which is accrete at the Eddington rate. Then the luminosity could be in the form of a jet, could be in the form of a wind. If it's in the form of wind, it could be launched magnetically, or it could be launched by heating. Okay. The luminosity is, G m black hole. Well, easy way to do this way I wrote it before. M dot. That's what it is. I'll just write as the Eddington luminosity. For one of these big holes, I'll scale it to that. It's 10 to the 46. Okay. Now, observationally, you don't really get much above the Eddington luminosity almost any kind of vision. Maybe you can get 10. Biggest I've seen is 100 times Eddington. So, accreting neutron stars in nearby galaxies, they're about 100 times Eddington. But their luminosity is 100 times Eddington. You have to do this for a while. The first one. I'm just saying you can beat the Eddington luminosity. Yeah. They may not be all due to accretion, but it feels so power vision. All right. Now, if you're putting it out in terms of photons, then the P dot, which is also called force, is just L over C. Okay. And I just want to compare that to that force up there. Okay. So if we're doing it this way, This is 10 to the 46, 3 by 10 to 10. By 10 to 25 dynes, I guess it is, right? Okay, what's this number? This is our same, 2 by 10 to the 7 squared, so 4 by 10 to 14. This was 10 to the 10, so that's 2 by 10 to the 43. This is, we'll call it 3 kiloparsecs because then it's easy. It's 10 to 22, 70. Okay. All right, so that's 8. It's 57. Right? Yeah. Okay. Well, sorry, 35. Right.
We lost it.
Last factor 10. 10. Well, so this is interesting because it says, right, if you use all the momentum coming out of the black hole, you can actually push the gas out. Well, that's what got some people all excited about radiation pressure outflows.
It's coincidental.
It's not completely obvious. It's total coincidence. Yeah. Okay, so that would be if you could capture all the light coming out of the quasar into the interstellar medium of the galaxy, you could drive it out. Well, that's kind of hard to do because the galaxy is kind of skinny, right? Most of the light's going to go above the disk or below the disk, and it doesn't really. I would say by and large, it doesn't really work. Okay? Now, the same argument works for winds, of course. Actually, winds don't come out in the direction of the disk; they're going to go above and below.
Is the relevant gas in this or is it above?
If you want to stop star formation anytime soon, it's in the disk, right? Because the consumption time for gas in the disk nowadays is 2 billion years, which is a long time. Back when these things were actually forming a lot of stars, it was maybe a little shorter, but it was, several hundred years. So you really want to get rid of it in the disk, because otherwise, the quasar turns on, it's only on for like tens of minutes. And then you didn't get rid of all the gas in the disk, and still make the stars. It takes a long time. So you really want to get it out of the disk. But this at least says, now you're in the ballpark, right? Whereas doing it energetically just doesn't. I'm halfway through and I haven't said a word about London. Let me keep going a bit more. So I should say another form of feedback is, of course, jets. And supermassive black holes produce jets. We see them all the time. But at jet luminosities. So this is also called electromagnetic, because that is typically 10 to the 46 ergs a second. That is a quasar luminosity. Those things exist typically in 10 and 12 solar mass halo, but typically which is also the peak star formation, by the way. So they're in the right place at the right time to get rid of the gas. So that's why people are interested in quasars. Now, some fraction of quasars have jets. It's only about 10%. And a typical jet luminosity is 10 to the 43 to 10 to the 44, so about 2 ergs per second. In galaxies that have 10 to 8 solar mass black holes. Bigger holes can have more powerful jets, but they're typically not as luminous in kinetic energy. It's kinetic energy. Well, originally it's point influx, but it turns into kinetic energy, as they are in light. Okay, and they're much more directed than the light is. Right? They're direct. They're fairly narrow. So I don't think they work very well as feedback in galaxies. They can't get rid of the galaxy jets. What they can do is what you were thinking, particularly in halos that are big, like 10 to 14, 10 to 15. I think there's no doubt that these things provide the feedback that produces the bubbles that you see in X-ray emission in nearby clusters. And they probably provide the feedback that offsets the cooling that you also see in the gas. So that's a form of what people sometimes call. So this stuff I was talking about here, that sort of feedback is quasar mode feedback. The other one is they call those jets. And there's some other modes. What's that?
That maintenance mode?
Well, it's basically a maintenance mode, yeah. It's trying to keep the gas hot so you don't put cold gas into the galaxies. Okay, so it's a preventive feedback as opposed to an objective feedback. And that does happen, I'm sure. Okay, but it's not very good for getting gas out of the disk. And I'm mostly focusing on getting gas out of the disk. Okay, so I've talked about a couple of feedback mechanisms. This is just radiative feedback. This is jets. And Chris already mentioned winds. And I think right now, most people sort of think it's winds that are painful. Right? So how do winds work? From black holes. We also have winds from galaxies that don't have black holes. They're produced by supernova, more or less, going off in the disk. Those winds will also gas from the disk, and we see that happen. They probably don't quench star formation. It might, but I kind of don't. I mean, like, certainly not quenching star formation in our case. We're not doing much in the way of star formation. We're doing slackers, right? 2 or 3 solar masses. But, and as I said, it takes 2 billion years or so to get rid of the gas. In the meantime, there's some gas coming in through this. So that'll keep going a long time. We're not going to be quenched for at least 2 billion years. So if you want to turn off the stars, you got to do that. So a black hole would be a good thing to do. So winds, how do you make winds? There's at least 3 ways, probably more. One is, again, if you produce enough X-rays, for example, which you do, these quasars are dominated by ultraviolet light, but they do produce a lot of X-rays. And you can heat the gas up to, you know, you see X-rays in these things, so there's already gas sitting there, 10 to the 7, 10 to the 8, 10 to the 8. That probably isn't going to do much work. You can produce a wind by what's called the Blanford-Payne mechanism, which is if you have these quasars, because you're seeing light coming out from regions of like 10 to the 15 or 10 to 16 centimeters, that's, you know, 10 to the 4 to 10 to the 5 Kelvin. That's way below the real temperature of that radius. So it's very efficient cooling. That's a thin disk. But it almost certainly has magnetic fields in it. And those magnetic fields can launch via this Blanford-Payne mechanism. Just basically, the idea is the magnetic field is strong enough that, you know, it pokes out of the disks and it's also going around. And if the angle to the disk is low enough, there's enough centrifugal force exerted on gas that's attached to that field line to accelerate it out. And that'll produce a wind. Okay. Another way to produce a wind is to use the same argument I was doing here. Use the radiation to push the gas from the surface of the disk, or in the vicinity of the disk, out. I just told you these things are typically sub-Eddington, meaning you can't push just on the electrons. But the Eddington limit is to say, for every proton you got an electron, radiation, when it's going out, it doesn't really see the protons, it just sees the electrons. Thomson scattering cross-section, you know what that is? If a photon hits it, the photon gets scattered in some other direction. On average, as much forward as backward, which means that the net result is you get 1 unit of momentum per that photon to push out in the gas. So that's the outward force. And this is just coming from balancing that outward force against the force of gravity from the black hole. Okay, but it's sub-Eddington, so you can't push the gas out of that. On the other hand, there's other forms or sources of opacity in this gas. And just so
It's sub-Eddington because there's a lot more mass in the galaxy than in the black hole, and this is Eddington maxing out of it.
this is the max of Eddington, but I'm now talking about a launching wind from the black hole close to the hole. So really, it's just the mass of the black hole that we're trying to find it's there to launch. And then I'm going to try to estimate how much momentum you get in that. And then I want to compare that moment to what you need to get the thing out of it. All right. And what the line locking, the reason it's of interest is this line locking refers to absorption lines. Typically, well, almost exclusively, as it ends up carbon-4, there's a transition. Carbon-4 is like you take all the electrons out, you have the 2 electrons in the inner shell, an S, and then there's another one in the 2s shell. Well, there's a transition between the 2s and the 2p levels, right? And if you take an electron, put it in the 2p level, go back down to the first one in 10 minus 8 seconds, very short period of time. And it turns out, of course, you remember this stuff, photon has 1 unit of angular momentum, so there's got to be a change of delta L, delta J, I guess, of 1. And so that means there's actually 2 transitions, slightly offset, okay, in frequency. That's true for hydrogen. It's true for helium-2. It's true for lithium. It's true for things like, well, what's after lithium? The next one, well, so the ones that matter for our case are magnesium, carbon, oxygen, and nitrogen. Okay, they all have a lithium-like state, and they've got 3 electrons. And they all have these delta transitions from the first excited state to the ground state. Those are called resonance lines because they take 10 minus 8 seconds. Okay, and so if you shoot a photon into one of these things, it's not going to collide with anything in 10 minus 8 seconds, so the photon's just going to. Okay, so it's a little different than your normal transition, like H alpha or H beta, where if you shoot a photon and it disappears. So these things, if you shoot a photon, it goes. So that's what's called scattered, and photons are destroyed. You get in the first excited state, but then a new photon, 10 minus 8 seconds later, comes out in some other direction. It's not the same photon, but it kind of looks like the same photon. So it's said to be scattered instead of destroyed and created. All right. So now I want to tell you about quasar phenomenology, spectrum. I think I'm just going to give it. I'm going to start drawing pictures of spectra. So we're shifting gear from sort of pretty simple physics to what at least I always found this impenetrable phenomenology. Because everybody I talked to who knew anything about this stuff just knew so much more than I did. So I'm just going to draw you some spectra of quasars. The observers usually use lambda, and I'm going to do it as lambda F lambda. So this is what you measure at your CCD these days, the flux energy per, what I use lambda is actually measured in terms of, they always plot this thing as a function of wavelength or frequency per square centimeter per second. Okay. And you can turn it into a luminosity just by multiplying by the known distance quasar because you know the redshift because you're going to see emission lines. Okay. So let's see if I can do this sort of reasonably well. There's a continuum, there's a line which is pretty broad, and there's another big broad line, and it comes up a little more, and it turns. You do it the other way. So here's some stuff. There's Lyman alpha here, which is really broad, and there's a little shoulder on it. It's smooth out from that. Another line, which is big, and it keeps going like this, and there's no way down that. You know, I forget how this thing breaks somewhere here. This is around 1,000 angstroms. Okay, this is 1215, so the scale is definitely not linear. Okay, this is alpha. This is nitrogen 5. This is 4. Carbon 4. Anybody remember this? This is 1550. This is oxygen 6. I got this back. That friction had a side there, sorry. This is 1,000 big functions. This could be something like neon 8. That's 7, 8. So, okay. So if you take a spectrum of a quasar, you can see something like this. Now, of course, you can't do this from the ground, right? In the ground, you can see down to about 3,300 angstroms. Well, except the quasars are high redshift, like 2, I said, right? So that means if you take Lyman alpha 1215, you got to multiply that by 3. That's 3,600. So you can see that from the ground, sort of. Okay, so you can see these lines pretty common. All right. If you add them all up, It's about 10%. Yeah, it's a lot. Well, okay, this typical width here, so maybe full width half max is 6,000 kilometers per second. Something like that. Yeah. Now this line is actually peakier than I've drawn it. It goes higher than I've drawn it. Because a lot of the flux comes out. So this is a big puzzle, right? 10% of the radiations come down in lines. How do you do that? It's not obvious, but it happens. Okay. All right, now, as I said, these are all these ones I've labeled. Every single one of them is one of these resonance transitions from the first excited state down to the ground state. Every single one of them. And that's just atomic physics. Okay? They look huge to photons. Okay. And one of the most abundant elements in the universe, well, hydrogen. Helium, I didn't draw any helium lines because they're not very prominent. It turns out sometimes you see a little bit of helium-2. But that's not a resonance. Because helium-2, the resonance energies, the resonance size is ridiculous. You need hard X-rays. So you just don't see heliums like that. It's called a noble gas, which just means it's snobby. It doesn't do anything. All right. These things are all doublets. Even Lyman alpha is actually a doublet. Just because it really is atomic physics. The line splitting for the doublet for this is 1 kilometer per second. Which you can't see. For this one, it's 498, below 500 kilometers a second. That's a little over 1,000. That's just short of 1,000. That's again right around 1,000 kilometers a second. Spin over. Yeah, exactly. 2.3 halves to P1 half. Right. Spin. All right. So these are all doublets. All right, so now I want to do a little more phenomenology. I have 15 more minutes here. In addition to this, very commonly you see what are called narrow absorption. Okay. And they'll be something like sitting in the middle of nowhere. You see these two little things that look like that. Okay. Assuming the galaxy's at some high redshift. And oftentimes, the most common doublet you see, not surprisingly, is carbon-4. And you can tell right away because the splitting is around 500 kilometers a second.
Same carbon-4 deposit.
Totally different deposit. Yeah. They can be redshifted or blue shifted. Normally they're blue shifted.
Do you never see narrow lines superimposed on the
Say again.
You never see narrow lines superimposed on the bottom?
You do occasionally, not too much in quasars. In Seyfarts, again, phenomenology, Seyfarts are like nearby tiny versions of quasars. They're typically, luminosity is 100 times less than quasars, 10 to the 44s a second. And there you often see very, very sharp narrow line regions. Very, very, in other words, like this thing would just go way up. Like this thing's an incredibly narrow line. Yeah, that's for a Seyfert. You don't see that in quasars.
So, velocities, the frequencies of lines, there is systematic shift.
Yes, there are. So, for example, the best you can tell, if you look at magnesium-2 and you look at oxygen-3 lines, for example, he's worried about, is this wind tied to the quasar? What's the wavelength? Or this sort of the breakdown to?
It's going to be a systematic.
Right. So the answer is like this carbon-4 line's a good one. If the equivalent width is not that big, so if you just add up all the photons in here, if that's not a huge number, that line is at the systemic redshift of the galaxy. But if you go to a large equivalent width, in the right sense, then it's blue shifted. But also it's asymmetric, it'll be like this. I'm kind of exaggerating. Shift get up to about 3,000 kilometers a second, so they're not trivial. Okay. And there's a systematic relation between the offset versus the equivalent. Okay. So what Chris is getting at is, if it's a wind, suppose it's coming from a disk. Like if the disk is like this for us, and the wind has to at least have some component coming at you. You won't see the one on the other side because it's blocked by the disk. And so you'll get a systematic blue shift. You do see that. So you could argue that, you know, the ones that are narrow and low with it like this, and the ones that are show the big blue shift, they're like that. And that's probably got something to do with it. All right, now the other thing you can do is you can say, where do these lines come from relative to the continuum light by using what's called reverberation method. So quasars aren't constantly the same light, they get brighter and dimmer randomly. And when they get brighter, you wait a little while, the lines get brighter. And when they get dimmer, you wait a little while, the lines get dimmer. And then wait a little while for like Lyman alpha, if you look at nearby Seyfarths, that's a couple of days. If you look at quasars, it's more like, you know, 10 days, a few weeks. And that lag scales with luminosity to the 1/2, which is what you would expect if they are in photoionization. What does that mean? It means you're ionizing hydrogen by shooting photons above 13.6 dB at it. You're knocking the proton, the electron off the proton. But there's plenty of other electrons around, so they recombine, and that produces Lyman alpha emission line.
Basically, fixed ratio of photon density. Yes.
And gamma over n is fixed. And if you just increase luminosity, you gotta go farther out to reach that equilibrium. So that just shifts the whole emission region out. Okay. So now we know how big the broad emission region is. It's typically for a quasar, you know, 10 to the 16 to 10 to the 17 centimeters. If you go from Lyman alpha to that one there, that's a lot longer. Magnesium 2, it's a lot easier to ionize away. You can't ionize away hydrogen 100% because, you know, once you get rid of all the electrons, that you can't do better than that. Magnesium, you can turn it to magnesium 4, and then there's like 0 magnesium 2, right? So it's easier to get rid of magnesium 2. So it has to exist way out, and the lag is much longer for magnesium. And it just goes with the ionization potential of that ion, the lag. And so that's all atomic distance. All right. I haven't said anything about winds yet. So these narrow absorption lines, I should have drawn it as Chris pointed out here. Now, you see these narrow absorption lines, and sometimes, like the way I've drawn it here, like if that's 5,000 kilometers a second, that's maybe 20,000 kilometers a second. You can see them over here. Okay. If they're way over here, they're really going close to the speed of light. Nobody thinks those are associated with the quasar. That's just some galaxy between us and the quasar, and you're seeing some gas in the galaxy blocking out the light. So if you see singlets, not doublets, you call it the Lyman alpha forest. Okay, so it's just stuff between us and the quasar. But the stuff that's close could be either one. Could be associated with the galaxy or could be beam. But it turns out that most of it, if you're less than 10 or 20,000 kilometers a second, most of it's got to be associated with the galaxy. The number counts, if you look at the number counts of absorbers versus that offset velocity, things like this is 0. It goes way out like this and comes down like that. And it goes flat. And this is maybe, you know, 10,000 kilometers a second, farther. Okay. This is just stuff between us and the galaxy. Stuff meaning galaxies. Or, yeah, it's mostly on the outskirts of the galaxy. And this stuff is associated with the galaxy. And it's mostly moving towards us. So it's blue shift. You see a little bit going towards the galaxy too, not much. Well, you think the astronomers got the redshift wrong?
No, but I don't say how can you have a measure.
Well, you can shoot stuff at the galaxy. And there has to be some info to the galaxy to start. Yeah. I mean,
It's not related to
It's-
itself.
it's presumably not related to the galaxy. So that's one form of absorption. There's another form, which we see very broad lines. Typically, it's not so far off. It cuts off the blue side of the carbon-4 line, and you see absorption like this. Okay. So there's redshifted emission and blue shifted absorption. And again, you see it in all these lines. You see it always, if you see it here, you'll always see it Lyman alpha. You'll sometimes see nitrogen 5, but it's kind of hard to tell because it's butt up against the Lyman alpha. You see oxygen 6, but less often. and about the same frequency. This you see much less frequency. Silicon-4 you see about the same frequency. Okay, so what this stuff is atoms, ions, I should say, they're coming at us at velocities up to 30,000 kilometers a second and higher between us and the quasar. And that's believed to be an outflow from the vicinity of the black hole. Okay, so that's one of the winds that Chris was talking about. That's a line drift.
So how are you measuring the momentum?
Not very.
With principally get a measuring photon momentum.
Yes,
But kinetic momentum to the photon.
that's right. The difficulty is, so what Chris is trying to say is, you know the depth here. So in some sense, you think you know the optical depth of carbon-4 ions. But to go from that to a column is not trivial, because you have to know, first of all, what's the abundance of carbon relative to hydrogen? Probably it's about so. The next thing you need to know is what's the ionization state of the gas? What fraction of the ions are in the carbon-4 state versus some other state? And both those things produce big uncertainties. But then it's worse because you don't know what the distance between the center of the black hole is and this outflow. So if you're trying to, for example, find a mass loss rate, you need to know that distance. The other thing is, you don't see this in all quasars, you only see about 20% of them, or maybe 30. Okay. So do you see these outflows in all galaxies? Are they in all galaxies? We just don't see them. It's pretty clear from the phenomenology that this is in every single quasar has these absorption lines, but we don't see them along the line of sight. The reason I say that is you look at every other property, these BAL quasars, to regular quasars, they look just like this. Now the other thing is, I deliberately drew it this way. This line is narrower and not that high, and this thing is deep. And remember, I talked about the equivalent width here. Means how many photons, compared to the continuum while they're in this line. The equivalent width of these absorption lines is typically 10 times the equivalent width. Okay. But I told you these photons are just scattered. So where are the other 90% of these scattered photons? They should show up here in emission. If you look at an O star, you see this almost the same thing. O star spectrum look like this. If you look at carbon-4, they go up, they go to the line center, and they drop like a rock to black. Sorry. They drop down gradually, and they go to black, and then they come up. That's different than the way I drew it there on purpose, because they look different. This is 3,000 kilometers a second. That can be 30 or 4,000 kilometers a second. This is about 3 times the escape velocity from the surface of the Earth. Okay. All right, now to go back to the momentum case. If you add up these BAL quasars, all the photons that are missing in here, it's typically about 1/3 of the luminosity, because there's a bunch of these lines. So that says that you can just take the L over C, as you said, if you would assume you captured all of it, but you don't. And then you multiply by 1/3, and that'd be the momentum. But then there's some cover factor. What angle are you actually capturing of those photons? So it's.
But you haven't explained to us where the photon.
Where they went?
Yes.
They went in some other direction. Because the wind isn't symmetric. Wind isn't a spherical wind. Like in an O star, the photons get scattered, they come out, and we'll see them in some other direction. Here, if you're looking down the pipe, if you see the wind coming at you, the photons preferentially get scattered up or back, and we don't see those. Okay.
But you never see broad emission.
If you look carefully, particularly in polarized light, you can see these really low luminosity broad emissions, which are those scattered photons.
You mean every bump there actually came from scattering?
Well, so that's an interesting question. How many of these photons are actually emitted and how many are scattered? Well,
So that's 10%. 10% energy.
yeah, 10% of the energy and therefore 10% of the momentum is scattered. So that you can put into the outflow. But that 10% of the none of the energy goes out. Because when you scatter, if you dump a lot of momentum from a very light particle and a very heavy particle, none of the energy goes out. So the wind doesn't have much energy.
I guess I'm confusing who the star line profile.
Well, I should have made it the same amount of,
Are the open widths the same?
yes,
Yes, sir.
that's I do. They're narrower, but they're higher, right? Like that. They're not, well, actually, they're about the same width. Yeah, but the equivalent width of these two is the same.
But most of it is isotropic.
Well, this says it is.
That one's,
And this one, just by looking at those line profiles, you know it's not isotropic.
that's good.
Also the absorption, would you draw the intention that this is an absorbing more on the right hand side? On the breakout and then the brand on the.
Can you go to black, you mean?
No,
Oh, you're
black.
saying the more absorption
Yeah.
here? Yes, I did that on purpose because that's what's observed. And actually, I think I understand why that is too, right? The optical depth, if you have a accelerating outflow, the optical depth, normally it's just, pi e squared, rev EC times some, F factor times, what's it, wavelength, the frequency wavelength, times the number of particles along the line of sight. Okay, but for a wind, this goes to the same. This is essentially cross section behind. For a wind, it depends on dBdr. Depends on how much you're smearing them out in velocity space. Okay. So when you launch a wind off the star, the gravity is really high right at the surface of the star. And as you move away, it drops off. Okay. So when you're close to the star, if you're going to get out, you got to accelerate hard because you got to be gravity. So dBdr is big. This is basically the acceleration. So the optical depth is low in an O star wind near the surface of the star. As it goes out, the acceleration drops off, dBdr gets smaller, and the optical depth goes up. I should have said it goes up. Okay, so when it's coasting at the end, you really get off the thick, and then the velocity stops, and that's where you get the sharp edge. Okay. It doesn't look like that at all for any quasar. And I think the reason for that is because it's being launched from the disk. Right? The disk is going around in circles, so there's no gravity effectively at the surface of the disk. So dBdr is really small in the quasar in launch it, so you get a big optical depth and low velocity. And then as you move away from where you started, you lose the rotational support, and the thing has to accelerate harder, and the optical depth decreases. All right, I still haven't got the line on. It's an hour.
What's some like what fraction of the process contains kinetic?
So I think it is probably about a 10 when you average over the whole thing. Yeah.
But the velocity is like the speed of light, but we have gas.
Say again. Oh, the velocity's, yeah, it's a tenth of the or less of the speed of light.
So you're getting them 2% kinetic.
Right. Okay, so now how do you know what's driving this? I mean, this I just said, that the light could drive that much out. You don't know that the light's driving it from the launch. Okay. And the line locking, just quickly go through the story. That's when you see two carbon-4 doublets on top of each other. Like that. Okay. And so the space, you can tell that because the spacing is 500 kilometers a second between these two explosions. Okay. And in fact, if you look at the spectrum, you can actually see even these broad absorption like quasars. You see this. There'll be some maximum absorption. If you look around that maximum absorption and you stack on top of that, which people have done literally 200,000 quasars, the line profiles actually show a shoulder. Okay, so this is 500 kilometers a second. This is carbon-4. Right, this one is twice as deep as the first one. It's up. And then there's another shoulder here, another 500 kilometers offset. Okay, so you've got that is an immediate signature of radiation pressure matter, line driving matter, and it tells you that the total acceleration can't be more than about 100 times the acceleration you get out of just the carbon-4. Maybe it's only about 30 or 40 times. Okay, because if the acceleration is bigger than that, you cannot get this line locking signature. I meant to explain all that, but I didn't get it. Okay. So this tells you that the radiation pressure on lines is the dominant acceleration in quasar modes. It's not coming from anything else. Okay, so that's a really striking result. So I'm going to go back and work through all the details of how the line locking works. I sort of done this in some. And it really is true. You can't have any more acceleration than you get just from what you see absorption in the spectrum, because then you couldn't see the line locking signature. So that then tells you, even though you can't measure the distance or anything else, it tells you how much momentum you have. Okay. It's just set by the single scattering limit, which is this L over C rate. So that's a really important constraint. So I'll stop. Questions?
That's probably the most important point. So why is like the shoulder, like the line mounting on top of powder is the stronger point of the line below?
So what happens? So the way you get line locking to work is, you know, so suppose you have say a smooth line, right? Which these continuum profiles show. Where every so often, even in O-stars, you'll see these. They're called discrete absorption. It's like that, right? If it's a doublet, you'll see a doublet. Like this is Lyman alpha versus the this extra absorption here, right? If there's, you know, at a higher velocity farther to the blue, there's gas there. Again, if it's doublet, you know, suppose it overlaps so that this doublet overlapped after like that, and you had two start out like this. There's a deep one, shallow one, and it overlapped because you're not too far apart in velocity with the other guy at lower velocity, deep here, shallow one there. Okay. Well, if this thing keeps accelerating, because the observer keeps planned accelerating, means this one moves away from that one. Because initially, when you're starting out, right, the acceleration as a function of radius from the star or the black hole starts low, it goes up, and then you kind of turn off. So initially, if you're farther away, you have a higher acceleration. So this gas is moving away from that gas in velocity. But when this one, you know, when this one shifts into this line here, this one's going to be starved of the photons from that one. It's going to be in the shadow of that absorption line. So that'll reduce the line driving on the faster gas. Okay, so it's going to accelerate, but not as fast as it used to. And if the total acceleration isn't too big, then that reduction in the acceleration of this line can actually cause the difference in acceleration, which should be some finite number here. This will produce an absorption trough, which could bring it down actually to that level or even below. Right? If it does, if you get down here, then this guy's slowing down relative to that one's going to come back till it reaches this point where the two accelerations match. When they do that, the lines are locked in velocity space.
So these are from different ions.
No, from the same ion, but the two different locations, right? So you got, you know, in the case of a star, you know, just think of it like this. Okay, you know, this is R1, B1, A1. And in the case of a star, we have drawn here, that's bigger than that. B2, sorry. R2 is bigger than R1, B2 is bigger than B1. And the way I'm currently thinking of it, it's A2 is still bigger than A1. So I'm in this part of the acceleration. Okay. In that situation, these lines are like this. They're going to come into this state right there, and they're going to get stuck there. So that's line locking. Okay. In principle, you should be able to get them all.
But like between, these are all doublets.
Yeah.
So you can get them all doublets.
You could get them non-doublets, yes.
But yeah,
That's
you
possible.
get across.
So, for example, you could get Lyman alpha nitrogen 5. So then move around and try to use
But observation.
the only one you ever see, believably, is carbon 4, and there's a reason for that. The reason is the splitting here is 1 kilometer a second. So that line, those doublets always shadow themselves. The next smallest splitting is carbon 4. And from there on, it goes up. So the first one you're gonna run into is carbon-4. So I think that's why you only ever see carbon-4 in
Two components are fairly close in proximity.
500 kilometers a second. That's close. Yeah. It's bigger than the thermal line, but which is not true for line locking, which is why you don't see line locking. But this is like 1,000 kilometers a second. Before that ion will cause you to travel this one.
So if subcarbon would fail, I could.
Then you could go to the others. The other ones to look for would be oxygen 6 and nitrogen 5. That one's hard to look for because it's blended. So the best one to look for would be that one. People have looked at it not seen it. But it's probably there. Some system. They had to not get locked in carbon. Now you will get locked into carbon-4 if you just have line driven. Because you can work out, total acceleration isn't that much bigger than the acceleration you get just from carbon. But if you have a magnetically driven, well, it depends on how strong. It's got to be strong. The momentum input's got to be stronger than line driving, because otherwise you just call it line driven. But if it's 5 times higher, you can't get any line, because the perturbation from this velocity splitting here, right? If you have more acceleration, this curve is higher, right? But the depth of this absorption is fixed by the atomic physics. So if you make the acceleration too big, atomic physics can't overcome the difference in acceleration between that velocity and this velocity.
No, I thought you initially wanted to drive outflow in 3 kilometers. This sound to me is still in
Oh, this is still just talking about a wind. I'm not getting anything out of this yet.
Oh,
Out of the aging, out of the galaxy.
Well, of course, one thing that you. Also is that black hole mass flow rates in college. It's very similar.
That's right.
There is a direct case for feedback in zero,
Yes,
less so.
for the disk. That's correct.
what's that mean?
That means it's easier to blow things out if they're spherically symmetric than if they're in disk.
Right, so this is.
So then you would expect it to correlate better with it.
This doesn't give you some after the spheroid more or less is the same.
That's correct. I think that's right. That's right. I think that's
So
but
by the time this is some way the black hole is doing. They still have to explain what happens.
yeah, and this won't do it. I think that's correct. So I didn't say I was going to give you an answer to explain how you got to the stars. I was going to explain how lilac can help you with driving. Yeah. No, I was just really struck by the fact that, when you have 200,000 quasar spectra, you can actually see the signature of line locking in broad absorption line troughs. It's really impressive. I mean, just stack the hell out of things. Find the maximum depth, stack everybody on top of that, and sure enough, a little bump shows up. Yeah.
75% of emissions coming from the line emissions, right?
Yes, right.
Yeah. And so that means that most of these line emissions coming from the regions close to the black hole.
Yes. Yes. You know that because of the reverberation.
Yeah. So and we can consider this region as an expanding region.
No, because if it was expanding, well, the lines, even including carbon-4, really, they're centered in this center direction.
That's what I was finding.
Yeah,
Like they have to be.
So that means the stuff is going around in circles in my mind. Okay, because what you're seeing then is, right, imagine you're looking at a disk, and it's going around in a circle, right? Well, if you look at this side, it's going like this. Going like that here, and it's going towards you there. This stuff you'll see is blue shifted, and that stuff you'll see is red shifted. And if you plot what the line looks like, it'll look like this, which is not what that line is, what those lines look like. So it can't just be the surface of the disk. If you look at cataphysical variables, this is exactly this. Double peak lines, where the separation here just corresponds to the velocity down near the center. Okay, the edges of the disk give you stuff in the middle here, because, well, and that's also the stuff here and here. Like there's no redshift. Okay. These lines are symmetric. Now, the reason they're single peak, I think, is because there is a line-driven wind coming out of this thing. And that makes it easier for photons to escape from these regions than it is to escape from these regions. The reason being, right, all you gotta do is move a little bit in velocity and you're out of resonance with the gas, and the photon can then just get out. Okay, so you suppress the emission here because, right, the wind is going in this direction.
I see.
Right, okay. And so that makes the line single peaked. Okay. But the overall center of the line is near systemic. Everybody's still here.
Okay, then, thanks again.